Okie donkey. Let's do an example. So arctan. You could use your LIPET rule, but really you don't have a choice here. Okay, you have to choose a U and you have to choose dV. If I choose dV is equal to arctan x dx, oh, that's not going to help me, right? Because I'm going to have to do an integral of arctan, which is exactly the original problem. So that is of no use to me. So I don't really have a choice in this case. I'm going to have to go with U is arctan and dV is, well, again, U is arctan and dV is whatever's left. So in this case, just dx. So derivative of arctan is 1 over 1 plus x squared. And when you do integral of 1 dx, you get just x. Oh, bye. Okay, so I plug things into my uv minus v integral v du, and here we go. Works out nicely. Now, what I notice here through experience and practice with substitution is that a substitution is going to work right here. Because I see that if I choose my u sub to be the denominator, then I will be in business. So that's what I did. So to do this integral, I did a substitution, okay, back to 5.5. And I worked it out. I'm not showing my steps, but you can do it, on the side here. Okay. While you're watching these videos, do not be afraid to pause and work things out. Okay, here's an exercise for you. I want you to try just ln of x. Same situation. You gotta choose a u and a dv, but you don't really have a choice. So pause and copy and try. Okay, here's an example. Oops, I lost my dx on the end. Here's an example that's a bit more interesting. What do we choose? U is equal to x cubed or u is equal to ln of x? Well, following our LIPET, we see that L comes before P. So we're going to choose u is equal to ln x. And dv is whatever's left. Okay, working out du and v gives this. Plug and simplify. Plug and simplify. Very important. I did some. Let's look at that integral v du. What did I get? I got x to the 4 over 4 times 1 over x dx. And I had to take a step and simplify. I mean, if you look at this thing and you don't simplify, you're going to be stuck. Okay, so you need to take a step and simplify as much as possible, and then reassess from there. Thankfully, this is very simple. Just a power rule. So I get from this, I get x to the 4 over 4. And 4 times 4 gives me 16 on the bottom. Et voila. Oh, here's a fun one. Here's a fun one. Here is a fun one. What time? Where are we? What time do I have time? Oh my goodness. Oh goodness. Oh goodness. Lots of time. Try not to make these videos too long, but I have time for this one. E the x sin x. What to do, what to do, what to do. What does LIPET say? I don't really think about LIPET, but I might as well be consistent for once in my life. it tells me that I should do the exponential. This should be u before I do the trig, the sine x. Okay, is that what I do? Yep, that's what I did. Well, it's not going to matter in this case, but thankfully I followed light bit. Okay, I make that choice. Work out my du and my v. And plug it in. And here we are. Now I notice that I get another integral that seems like a biparts integral. Seems like a biparts integral to me because you have a function times a function, and there's not really an obvious inside function. Okay, obvious inside function would motivate me to try substitution. Not in this case. So I'm going to try biparts again down here. I do so. Here we go. Same kind of choices I made up here. Okay, u is the exponential, dv is the trig. It's important that I be consistent, okay? That's a detail, but I chose u to be e to the x here. Unfortunately, it's going to matter. I'm going to need to choose u to be exponential down here too. Okay, work it out. Du and v. And then use my biparts formula to write that down with my square brackets. So important. So important. I'm going to boldface them. Now, what's happened here? Well, I'm going to erase my brackets. It's actually not important in this case because coincidentally I got a plus here. Now what's happened? I've come back to where I started, right? This integral, which I have produced, is the same as the original integral. Oh boy. So it seems like I've kind of boomeranged here, but this is a good boomerang. In fact, we call this integral a boomerang because look what we have. Not obvious. This is not obvious, this next step. We have found with this result here, like you've forgotten what's sitting over here. Okay, it's the original integral, right? So we found the original integral is equal to all this stuff. Now, the not so obvious part is to take this guy and move it over to the left-hand side. When you move it over, this minus sign becomes a plus sign. Oh. And you basically double this integral over here. Okay, so again, this item here moves to the left-hand side. So you get this integral plus itself, giving you 2 times the original integral. And what are you trying to find? You're trying to find the original integral. So let's divide both sides by 2, and we're done. I did a few more things over here. I factored out e to the x, and I put the sine x first because it was plus. I like my pluses before my minuses, but the main step to go from here to here was just dividing both sides of this equation by 2. So this is what's called a boomerang. Okay, your original integral came back. And sometimes that's a very nice thing because it allows you to solve as I did here. Okay, to close out this video, here's an exercise. And I want you to do this integral twice. First time, I want you to use integration by parts. It will be a boomerang. And the second time, the substitution, u is equal to ln x. Okay, so pause, oh, don't pause, just try that, and we'll talk about it in the next video.